Okay, in this series of videos, we're going to start taking a look at what physicists call simple harmonic motion. So that end, we'll first start by just doing a quick review about how springs work. So let's say I have a wall and I attach a spring with spring constant K to it like so. And let's attach a mass like that. If I were, oops, do a little better job of drawing that. There we go. If I were to pull the mass over to the right from the equilibrium position, so this is the equilibrium position here, which we'll say corresponds to x equals 0. Anything to the right of, if I pull it over to the right, we'll say that this is x positive, or we stretch the spring. And if I were to compress the spring, we would say that that's x negative. So in that case, the force exerted by the spring will be equal to minus kx. And here, when I talked about springs before, I didn't make a big deal about the minus sign. I said you could drop it, you could just use your intuition to figure out which way the force is pointing. Here we're going to need the minus sign in order to keep track of things. So the deal is that if I pull something to the right, the spring, if I move something over to the right here, the spring is going to try to pull to the left to bring it back to the equilibrium position. So x being positive, I need the force to be negative. So, okay, minus sign checks there. Similarly, if I compress the spring, x negative, the spring will have to be pushing to the right in order to get it, to try to push it back towards the equilibrium position. So put in a negative here, minus a negative is a positive. Again, the sign checks. So this is an example of what we call a restoring force, which means that is a force that is attempting to restore something to its equilibrium position. And again, just as a quick reminder, there is a potential energy associated with springs, and that turns out that the energy associated with the spring is 1/2 k times the square of its stretch. So it doesn't matter if you're stretching it or compressing it, because the square will make the number positive. And this is one of those cases where we have set the potential energy to be 0 at x equals 0 already. So you're not free to choose somewhere else to be 0. This is one of those cases where a choice of where 0 should be was pretty much forced by the methods of calculus used to derive this result. Okay. So with that, if you think about what happens if you've got a mass attached to a spring and you start letting it go. Let's say I compress it and I let it go. So here's the equilibrium position. At first, when you're out over to the left, you're going to be feeling a force to the right. And so it's going to move over. Well, how's the energy budget for that going to break down? Well, here it was all the energy was potential. Here, the spring still has some stretch to it, so there's still some potential energy. Maybe about like so. And we'll have some kinetic energy. When we get to the equilibrium position, here, there will be no no potential energy. It will all be kinetic. And then similarly, let's say when we get all the way out to the other end, so as we continue to head over, now kinetic energy will decrease and potential energy will increase as we stretch the spring until we get out to some sort of maximum point here, where once again the energy will be all potential. Alrighty. So this, so there's a maximum stretch that the spring can have, because if I were to go any further, this would require the kinetic energy to go negative, which can never happen. So we say that this maximum distance from the, from the left, or the maximum distance you can stretch it, is the amplitude, and we'll use a capital X here to denote that. A lot of books will use a capital A for amplitude. Same difference. So, and then what's just going to happen is this is going to turn around and bob back. So we're going to go back, forth, back, forth, back, forth. So these extrema here are also known as turning points. Because they turn around and go back there. So what we would like to do is come up with some sort of a function. We would like to find the position as a function of time. And it turns out that even if you were to use the methods of calculus, the only way you can do it is to guess and check. So what all do we need to satisfy? We need to satisfy, we'll do guess and check. And so we need to satisfy Newton's second law. That says that A equals F net over M. The only force is the spring, which is minus kx. So this will be minus k over m times x. So as we go through, whatever expression we have for x of t, when we figure out what the corresponding expression is for the acceleration, they better be negatives of each other with this proportionality constant. They have to satisfy energy conservation as well. So we are going to demand that the total mechanical energy, which is equal to kinetic plus potential, they'll equal 1/2 mv squared plus 1/2 kx squared. That has to be equal to a constant. And then finally, we have to satisfy the definitions of velocity and acceleration. So when we figure out the velocity, and earlier here, when we were figuring out the acceleration, in addition to satisfying these constraints, we also just plain have to satisfy the requirements that the acceleration be at any time be the slope of the velocity time graph at that same time, and that at any time the velocity be the slope of the position time graph at that time. Like I said, the only way we can do this is to do guess and check. So I'm going to make a guess here, and I'm going to feel very lucky about this guess. I'm going to guess that the position as a function of time will be equal to the amplitude times the cosine of 2 pi t over capital T, where capital T is the period of oscillation. So the period of oscillation is going to be the time it takes. If we go back here, say if I stretch it out here, let it go, it'll be the time it takes to go here and back. That would be 1 period. So that's my guess. I am feeling incredibly lucky about this guess, but we do need to check it. So my strategy here is I'm going to start with the definitions. So I'm going to try to find corresponding functions for the velocity and the acceleration, and then I'm going to, once I find those, I will plug everything into energy conservation and Newton's second law and see if it all works out. So at first blush, this might seem awful, like there's absolutely nowhere you could go with it. But at some point along the way, somebody made a very clever observation. Let's say we have a wall here, and we were to take a mass and tie it onto a string, like so. And then way back here, we have a light source shining on it. If we have the mass on the string going around in a circle at angular velocity omega, it would be cast its shadow here. So if we look at the shadow of the ball, the x-coordinate, the x-coordinate of the shadow is the same as the x-coordinate of the ball on the string. And so we know what that is. If we say the string is of length x here, we can write that x would be equal to, as a function of time, be equal to this x times the cosine of this angle theta here. But this angle theta, if we say t equals 0 right when we were at max, when the ball was here to begin with, this theta would be equal to omega t. All right, that's cool. But omega, we can figure that out. If this is going around uniformly in a circle, it would cover 2 pi radians in 1 period. So if I stick that into here, we get that, yeah, the position of the shadow here would be x times cosine 2 pi t over my period. So, hey, that corresponds to my guess for that mass on the spring. But here's the thing. I know how to find the velocity and acceleration of this ball. And so if my mass on the spring is following that function of time, then the shadow of the ball, if I can find the velocity and acceleration of the shadow of the ball, that would have to be what my mass on the spring is doing. So let's go find those. So we'll start by trying to find the velocity of my shadow. There we go. Now I know how to find the velocity. Whoops. There we go. I know how to find the velocity of my ball because I know at any given time its velocity will be equal to the tangential velocity. All right, so what we have to do then is figure out what is going to be the x component of this velocity. So this piece right here that I'm drawing in red, that would be the x component, my tangential velocity, and that would have to match the velocity of my shadow. All right. Now, by opposite interior angles, this angle here is that angle there, right? And since this is a right angle, that makes this the complement of this angle. And since that's a right angle, that makes this the complement of that. And the complement of the complement is the angle. So this angle right here is that angle there, is that angle there. Well, this is the opposite. So that means that the velocity of my shadow, which would be the x component here, we pick up a minus sign because we're going to the left. It would be the tangential velocity times the sine of omega t. But we remember that the tangential velocity is always equal to the radius times omega. So here the radius is capital X. We'll say times omega. And we remember still that omega is 2 pi over the period from before. So if we put all that together, this is going to be 2 pi x over the period. And we can in fact write that v of t would be equal to minus 2 pi over t x sine of 2 pi t over t. So that's the x component of the velocity of this ball, which is the velocity of my shadow, which would have to, if my guess for the velocity of the mass on the end of the spring is correct, that's what it has to be in order to satisfy the definition of velocity. Now we can work out what this what the fastest my speed my mass on the spring can ever have, and that will be as you're passing through the equilibrium position. And this is because sine goes between -1 and 1, so the biggest thing it ever be would be this right here, 2 pi x over t. Okay. And we can play a similar game for the acceleration. And in fact, I'll ask you to pause the video and try it for yourself. And then we'll get back together and I'll go ahead and do it. All right, so here we go with that. So we know that if we're going around a circle at a constant velocity, if we go around a circle at a constant velocity, the acceleration has to be pointed into the center of the circle, and that'll be a centripetal acceleration. Again, the velocity of the shadow here is going to be the x component of the velocity of the ball. So I will draw the x component in red again. So this is the x component of my centripetal acceleration, and that would be the acceleration of my shadow. So to figure out components here, we can use alternate interior angles. Again, this is congruent to that, so there's going to be a cosine involved. So the acceleration will be minus the centripetal acceleration times cosine of omega t. And again, here we can remember that a centripetal acceleration is always equal to radius times omega squared. And we still have that omega has to be 2 pi over the period. So putting that all together, this is going to be 2 pi over the period squared. My radius is x, my amplitude, right? I'll take that and plug it into here. That will give me an acceleration equal to minus, again, minus because we're pointing left, 2 pi over the period squared x cosine, sorry, capital X here, let's do a better job of that, cosine of 2 pi t over t. Okay, So that's my expression for A of t. And again, this is just what has to be in order to respect the definitions of acceleration. So, with that in place, we can start to work out whether or not we are satisfying Newton's second law of motion. So remember, to satisfy Newton's second law of motion, that said that A is equal to F net over m, and our net force was minus kx. So let's go and put in our expression for A, and we'll put in our expression for x, and we'll see under what conditions we could possibly have equality. So our expression for A is going to be minus 2 pi over t squared x. Whoops. Cosine of 2 pi t over t. And this will equal minus k over m, and then we put in our expression for x cosine 2 pi t over t. Hey, check it out here. The cosines cancel, and the x's cancel, and the minus signs cancel. So it's possible for us to have equality, but we do have a constraint on that. The constraint here is going to be that 2 pi over t squared equal k over m. So this would require that 2 pi over t be equal to k over m. Now, what we often do is we define the frequency f to be 1 over the period. So this is the number of seconds per oscillation. This will be the number of oscillations per second. We usually write as a unit Hz, which is equal to seconds to the minus 1. Hz is read hertz, and we use that instead of seconds to the minus 1 in order to avoid any possible confusion with radians per second. So this would be saying that 2 pi f equals, square root there, equals square root of k over m. So in order to satisfy Newton's second law, what we get is it's possible, but we are now stuck with a particular choice. Okay. So now let's go and take a look at energy conservation. Remember, we said that kinetic energy plus potential energy at all times had to be equal to a constant. So let's start to figure that out. It's going to be 1/2 mv squared plus 1/2 kx squared. What's that going to equal for us? So 1/2 m. Remember, our expression for v was minus 2, minus 2 pi over t times x sine of 2 pi t over t. There we go. And we'll be squaring that plus 1/2 k. Now we'll just put in our expression for x, which would be x cosine 2 pi t over t. And we'll be squaring that. All right, so let's do the squareds. When I square, so I'll have 1/2 m. When I square this, the minus sign will drop. I'm going to have 2 pi over t squared x squared sine squared of 2 pi t over t plus 1/2 k. Squaring this will give me x squared cosine squared of 2 pi t over t. All right. But we've got this 2 pi over t here, and we remember that we had this constraint that had to be equal to root k over m. So let's go ahead and observe that everything inside the square has to be equal to root k over m. So then when I square that, this whole expression is going to just be k over m. So let's substitute that in. So I will have 1/2 m times k over m times x squared sine squared 2 pi t over t plus 1/2 k x squared cosine squared 2 pi t over t. M's cancel. Hey, now every term's got a 1/2, every term's got a k, every term's got an x squared. I'm just pulling those out. What I'm left with is sine squared of 2 pi t over t plus cosine squared 2 pi t over t. And we remember from trig that sine squared of any angle plus cosine squared of that same angle is equal to 1. So we get that the total mechanical energy is 1/2 k times the amplitude squared, which is indeed a constant, and in fact is the potential energy at maximum stretch. So sure enough, it all works out. Our guess was correct. So let's just explore for a second what those functions look like, and then in future videos we'll do some application. So let's start by making a graph. We're going to make 3 graphs actually. But we'll start by making a graph of position as a function of time. There we go. So this is position, that's big X, that's minus big X. And we were saying that this will go as a cosine. So if we say that this corresponds to a period of oscillation, then this would be half a period, this would be a quarter of a period, and this would be 3/4 of a period. The position as a function of time is going to be a cosine, and then it'll just go on and repeat. All right. And from our expressions that we found, we can get the velocity as a function of time as well. So now I'm plotting velocity. So this would be equal to 2 pi x over the period. That'll be minus 2 pi x over the period. Again, t over 4, t over 2, 3t over 4, and t. So the velocity is going to go like this, because it's minus a sine function. So it'll be a sine wave, but upside down. Something like that. And then finally we can do the acceleration. So again, that's t over 4, t over 2, 3t over 4, and t. So then we said that will be minus a cosine. We will be going between 2 pi over t squared times x, and minus 2 pi t squared times x. And that will be a negative cosine. Whoops. So, my bad there. There we go. So that will be a negative cosine. So that'll look something like that. All right, now the thing to look at is just to double check everything and see if we feel good about it. So we remember that at any given time, the value of the velocity is the slope of the position time graph. Well, here the slope is 0, the value is 0, that checks. Here the slope is a maximum negative, the value is a maximum negative, that checks. Slope 0, value 0, max pos, slope 0, value 0. Then we remember there's a similar relationship between slopes and values between velocity and acceleration as well. So let's check that. So here, slope is max negative, value max negative. Slope 0, value 0. Max positive, slope 0, value 0, max negative. So yep, it is indeed all checking out. So in future videos, we will go ahead and explore this further and do some application. Catch you on the flip side.